So, last time we dove deep into the mechanics of recursion. Today, we're going to take that concept and turn it into a full-blown strategy. We're moving past just the how to see the way recursion fuels one of the most powerful problem-solving patterns out there: divide and conquer. And this isn't just some clever coding trick. It's a completely different way to think about difficult problems. It all starts with asking one simple but really profound question.
That question right there, that's the whole game. What if our natural instinct to just charge at a huge problem head-on is actually the slow way? The divide and conquer strategy says, hey, maybe the best path forward is to break things down first. It's the core idea behind some of the fastest, most efficient algorithms in the world, and today, we're going to see exactly how it all works.
Okay, so how do we actually put this idea into practice? Well, the beautiful thing about divide and conquer is that it's not some vague philosophy. It's a clear, repeatable, three-step formula that you can apply over and over again.
Here it is, the blueprint. First, you divide. This is all about breaking the big problem down into smaller, bite-sized versions of itself. Then comes the conquer step, and this is where recursion really shines. You solve each of those little subproblems, usually by applying the same logic again, until the problem is so tiny it's just obvious. But what good are all those little solves pieces? That's where the third, absolutely critical step comes in: combine. You have to skillfully merge all those individual solutions back into one final answer.
And you really need all three. It's a package deal. For an algorithm to be a true divide and conquer algorithm, it has to follow this pattern: divide, conquer, and then combine. If you're missing one of those, you're probably looking at a different kind of strategy, though, as we're about to see, some pretty interesting variations do exist.
Now, you might be thinking, this seems like a lot of extra work, right? Why would we break something apart just to have to put it all back together again? Well, the reason is all about efficiency. It's a deep insight into how work grows, and it's the key to understanding why breaking a problem down is almost always faster.
This really gets at the two different mindsets. A brute force, or linear, approach is like trying to sort a giant pile of 1,000,000 books all at once. The amount of work just explodes. But the divide and conquer approach is smarter. It knows that sorting two separate piles of 500,000 books, and then merging those two sorted piles, is way less work overall. The cost of solving a problem doesn't just double when the problem size doubles, it can grow much faster. By breaking it into smaller pieces, we avoid that massive explosion of work.
And this chart really drives the point home. Look at that difference. As the problem gets bigger, the time it takes for a brute force approach goes through the roof. It can become completely useless. But the divide and conquer approach, it scales so much better. That huge performance gap is exactly why this strategy is so fundamental in computer science.
All right, enough theory. Let's make this real. We're going to look at the textbook example of a divide and conquer algorithm, merge sort. It's the perfect showcase for our three-step pattern. So, we start with a really common problem, a completely jumbled list of numbers. The goal is to sort them. Now, we could try to compare every number with every other number, but that gets slow fast. Merge sort shows us a much more elegant way.
Let's walk through the pattern. First, the divide step kicks in. The algorithm just keeps splitting the array in half, and in half again and again, until it's left with a bunch of tiny little lists with just one number in each. And believe it or not, that's the conquer step. I mean, a list with just one item is already sorted, right? It's the base case, and recursion handles all of that splitting for us automatically. But now we have all these tiny sorted lists. How do we get back to one big sorted list? Well, that brings us to the most important part.
The real magic, the secret sauce, happens in the combine step. The algorithm starts working its way back up. It takes pairs of those little sorted lists and merges them into a new, slightly bigger sorted list. And because it's always merging two lists that are already sorted, the process is incredibly efficient. It just has to look at the first item in each list, pick the smaller one, and repeat. This structured, methodical merging is what gives merge sort its incredible speed.
So what does all this get us? Well, some really powerful guarantees. First, its performance is super predictable. Unlike some other sorting algorithms, it doesn't have a worst-case scenario that suddenly grinds to a halt. It's also stable, which is a fancy way of saying if you have two equal numbers, they stay in their original order. For some tasks, that's absolutely critical. All of this makes it a reliable workhorse algorithm.
Okay, so we've seen the classic pattern in action, but now let's explore a bit. How can this formula be adapted? And, just as importantly, where does it break down? Because this approach is not a silver bullet for every single problem.
A fantastic example of a variation is an algorithm you probably already know and love: binary search.
You might not have thought about it this way before, but it's totally a form of divide and conquer.
Just look at how it fits the pattern. The divide step is when you check the middle of a sorted list and decide to throw away one entire half. The conquer step is just repeating that process on the smaller half that's left. But notice what's missing. There is no combine step. You don't need it. The answer is just found directly. This is a great example that shows that while the 3 steps are the classic formula, some really powerful algorithms can get the job done with just the first 2.
This brings up a really important question. If this strategy is so powerful, why don't we just use it for everything? When is it actually the wrong tool for the job?
There are really 3 main ways this can go wrong. First, you can have too much overhead. For a really small problem, all the work of splitting it up and managing the recursion can actually be slower than just solving it directly. Second, the subproblems might not be independent. Imagine if solving the left half of a problem actually changed the right half. You can't conquer them separately. And finally, the most common trap is an expensive combined step. If putting the pieces back together is just as hard as solving the original problem, then you haven't really gained anything, have you? The whole strategy only works if dividing is cheap and combining is efficient.
So let's zoom out and pull this all together. When you step back and look at the big picture, what's the fundamental idea we should really take away from all this?
This table really says it all, doesn't it? The brute force approach thinks in a straight line, and its performance just breaks down as problems get bigger. Divide and conquer, on the other hand, thinks recursively, and its performance scales beautifully. It's a fundamental shift from tackling a problem head-on to strategically deconstructing it first.
And this really gets to the heart of it. Divide and conquer isn't just about breaking problems into pieces. It's about controlling complexity. It's a method for turning one overwhelming, confusing challenge into a series of smaller, predictable, and manageable tasks. It's a mental model that works for so much more than just code. So the real question I'll leave you with is this. What big, complex problem in your life could you solve if you just stopped trying to solve it all at once?